So if you notice on that first example here, certain states' population is declining at a rate of 2.6 annually. The state currently has a population of approximately 11 million. The population continues to decline at this rate. Predict the population of the state in 15 years. What's our initial condition? What's our initial value, this n sub 0? 11 million. Yeah, we're starting with 11 million people. So we're going to write the equation. We're going to have 11. We don't have to put the million in there. We can go back and add that in. And so then we're going to have 1. It's declining, so it's going to be 1 minus. We got to rewrite that 2.6% as a decimal, right? Remember, we're going to write R as a decimal. So that means we're moving the decimal place 2 places to the left. So we're subtracting 0.026. And let's write the basic equation first, but then let's go back and let's plug in and actually do the math here. So y is equal to 11 times 1 minus 0.026 raised to the 15th. Okay. Do you see how we're kind of plugging in the parts there? I hope. All right. Plug into the calculator. What do we get for that answer? Let's round to, I don't know, let's round to like 3 places after the decimal. What do we get there? Alec, what did you get?
7.4.
Keep going.
7.4093.
Okay, so 7.409 million. That reminds me, we've done a hard clear in here a few times lately, and I need to refresh your memory on how you actually convert and switch your calculator back to float 12 and stuff, because the hard clear, some of yours are just a different setting for other reasons too, but I want to go over that with you. I've got this up here, so I want to kind of talk you through that process to make sure you understand. Carly.
Is this formula kind of similar to like the percent change formula? Because it looks the same.
Yes. Usually with percent change, you're talking about finding the difference from like the new amount, subtracting the original, that type of thing. And you're kind of going to have to do that every once in a while where you're finding differences in a couple of places. But yeah, I like that you're seeing that connection because it is similar. Yes. Great observation. I like it. I like it a lot. Okay, let's look at this next one. Here, this state, the population is increasing. And so we're starting with 11 million people again. In this case, we're increasing, so we know we're going to add. And that 3.4% has got to get written as a decimal. So it's going to be 0.034 raised to the x. And once again, we're looking at 15 years. So y is equal to 11 times 1.034 raised to the 15th power. Let's plug that in. What do we get? 18.16. Let's go to 3 places. So 164 million. I like it. Thanks, Claire. Okay. Actually, let's do that now. Well, no, never mind. Okay. All right, half-life formula. You're going to see this written in your on your My Math Lab. It's going to be written in a little bit different format. It means the same thing though. In the My Math Lab for a couple of the problems, they have 2 raised to a negative power. And if you think about it, if we have 2 raised to a negative x power, then if you think about that, we would rewrite that as 1 over 2 to the x, which is essentially the same thing as what we have here. So this is the way I'm going to suggest that you think about the half-life formula. So A, which is our initial condition again, obviously if we're talking half-life, it's going to be 1/2. And then we need to talk about the X and the T, because we need to make sure we kind of understand which one's which. So the X and the T, for the X, that is giving you the time span that you're supposed to consider. The T is giving you what your half-life is. So this sounds weird to say, but it's the half-life life, right? So I'm probably gonna write that a little bit differently. It's the half-life time. And you'll see that in this example here in a second. Hopefully you're going to be able to understand how to distinguish between the two of these. We're going to talk about A here in a minute, because that's kind of we're going to talk about how we set that up. We're not going to be able to solve this one yet, though. So we're going to plug into B first, and then we'll go back and talk about A for a minute. So approximately what percentage of 100 grams will there be in 40 years? So we need to go back because I didn't read this part up on top. A radioactive substance has a half-life of 16 years. So the 16 years is the half-life life, or the half-life span, or the half-life time. So that's our denominator, right? So we have 100 grams that we're starting with. And we want to know how much is left after 40 years. So we're going to do 40 over that 16. Okay. Please be careful plugging that into your calculator. That fraction is an exponent. You may want to use parentheses around that. Do me a favor and plug that in. You guys plug that in, because in my earlier class, one person got a fraction for that because he plugged in with the 1/2. And I'm curious if anyone else gets that. Everyone else got a decimal, but if you get the fraction, I want to be able to talk to you about how you do that. So try that for me.
I got the square root of 5 over 40.
I got 17.6.
Okay, good. You should get, it should be about 17.68, and so it would be grams, I think. But Alec, let me see.
I typed it in wrong.
Type something in
I
wrong.
didn't work with one. I said it.
Okay, so you have a couple of options at this point. You can either do Control-Enter to get the decimal approximation for that. The other option, see, you're truncated here. You're not going all the way out. So we gotta change our settings. Okay, the other option is from the get-go, instead of plugging that in as 100 times that 1/2 as a fraction, plug it in as 0.5. And try that. That's what that worked for Ethan earlier today. Okay, so try that and see if that works for you.
Yeah, that worked.
Okay. Anyone else get the weird fraction when they plugged in? I don't know if it's a setting. I'm trying to remember what type of calculator he was on. I don't remember if it was a CAS or not. Anyway. Okay, let's talk about letter A just very quickly. Where are we going to plug in this stuff? Where's the 100 going to go and where's the 30 going to go? Go ahead, Sharon. Okay, so the 100 is the A. And we know we have a 1/2. Where's the 30 going, Sydney? It's either X or T or Y. Which one is it? Yeah, it is. Good. Yes, exactly. So we're saying we're starting with this 100 and we're have this half-life until we get to the 30. So that's actually the Y value in this case. All right, we have, what do we have? The half-life is still 16, so we have X over 16. Okay, we are not talking yet about how to solve this algebraically using logarithms. We will on down the road, so we're gonna come back to this problem in a little while. But we wanted you to see this. We wanted you to think about some other ways that you can actually come up with answers. So the other option for solving this particular type of problem at this point, because you don't know how to solve, is we could graph this. We could plug it into our graphing calculator. We could plug in y is equal to 30, and we could plug in y is equal to this 100 times 1/2 raised to the x over 16, right? If we plug those two graphs onto the calculator on the same graph screen, then we can look at where they intersect. And that gives us some information there about how to solve that problem. So I just wanted to mention to you about that, just for those of you who are curious about how we could solve this, okay? But we're gonna move on. All right, did everyone got that 17.68 grams, right? Okay, cool. A couple more examples here. This kind of walks us through the process a little bit more, which I think is good. It's a little bit helpful. So it's kind of reminding us, here's our model, y is equal to a times b to the x. B, if it's a growth factor, means we're adding that, so we're doing 1 plus r. So this is asking us to figure out what the growth rate is. So it says population of U.S. in 1994 was about 260 million. God, that just sounds crazy, doesn't it? With an average annual rate of increase of about 0.7%. All right, so we've got our 260 to begin with. 1 plus, how are we going to write that rate? 0.007, good. So 1 plus 0.007, all raised to the, well, in this case, just the x, right? Actually, here they were just looking for you to do the 1 plus 0.007. I jumped the gun. So that goes here. Okay, so if the growth rate stays the same, what would the population be in 1997? We have to figure out what the span of time is that we are looking at. So we've got to do this 1997 minus this 1994. So we know we're going to plug in 3. So 260 times 1.007 raised to the 3rd power. So what do we find? I don't remember. 265.498 million people. Crazy. It's messy. Sorry, guys. Okay. Here's a depreciation or a decay situation. So you buy a used car that costs $11,800. Expected depreciation of the car is 20% per year, that's not very good. That's abysmal, actually. Estimate the depreciated value of the car after 6 years. All right, so what's our starting condition? Ethan, what's our starting condition?
11,800.
Yep, the 11,800. And then we're doing 1 minus, that 20% has to get written as a decimal, so that's going to be what, Lily? Move decimal 2 places to the left.
0.2.
So 0.2, good. And we're estimating this after 6 years. So if you want to plug that in as 1 minus 0.2, you can on your calculator. If you want to do the math and write that as 11,800 times 0.8 to the 6, that's fine too. You should still get the same thing. Now, we're talking money here. So $3,093.30. hang in there a little bit longer. One last little concept we're going to look at today. So we're going to use it more tomorrow, okay? We're going to look at exponential equations, and as I said, we're going to talk about how we solve them on down the road next week. Some equations can be rewritten in a general format that makes it pretty easy to solve. Basically, can almost do them in your head, basically. So that's the type of problem we're going to look at today, okay? So exponential equations are equations that have a variable as the exponent. So it'll be something like 4 to the x equals 16, or I don't know, what did I write? 3 to the, I like that, 3 to the 4x equals 27, something like that. So that's what exponential equations look like. You can see some down here at the bottom. We can use what's referred to as the property of equality to kind of help us solve in some instances. It won't work all of the time, but I want you to notice what's kind of special about these. So we're kind of giving you a writing in here that you can do this process. It's not going to say that all of the time though, right? It's just going to say solve these exponential equations. So you're going to have to be able to look and determine if you can do this process with them, okay? All right. Oops, I'm jumping the gun. I'm just getting excited. Okay, I want you to look at, I think the easiest way to kind of see or understand this, what the idea is here, is by looking at this down here. So if it says, if we have 3 to the x is equal to 3 to the 5th power, right? So our bases are the same. So what that's telling us then is that obviously whatever's going on, those two things have to be equal to each other. The exponents have to be equal, right? If we have the same bases, we have stuff that's equal to each other, then obviously the exponents are what has to be equal to each other. So that's the idea of what we are looking at here, okay? We're going to use that idea. So to solve each of these equations, we're going to rewrite each equation so that both sides of the equation has the same base. So you have to decide what that base is going to be, and then you just rewrite using exponents, and we can solve from there. Some of these are simpler to see than others, so we'll just kind of take a look. If we have 3 to the x on the left-hand side, hopefully it makes sense to you that we're going to rewrite that 9 then. Let me change colors here. Let's rewrite that 9 as 3 squared. That way we have the same base. So 3 squared is equivalent to 9, and that 9 was getting raised to the 4th power, right? Do you see that? And then our rules of exponents tell us, I'm sorry, let me rewrite this. So we have 3 to the x equals, our rules of exponents tell us we multiply. If we have a power raised to a power, we multiply there. So we're going to multiply that 2 times 4. So now our property is telling us, okay, well, if 3 to the x equals 3 to the 8, then x must be equal to 8. Okay. Take a look at that. Questions or comments or thoughts on the process or what we're doing there? All right, so let's look at a couple of examples here. So first thing to decide is what base can we use. For some of them it becomes pretty clear pretty quickly, but for others not so much. On this one, hopefully you recognize we have 2 and we have 4 as the bases right now. To rewrite any of those, we're going to need a base of 2. So we're going to keep this the same, so the 2 to the 5x equals. We got to rewrite this 4 as 2 to some power. So we're going to rewrite that as 2 squared. So that gives us the 4 part of it, but then we still have that 2x minus 1. Guys, we have to distribute there. So we get 2 to the 5x equals 2 to the 4x minus 2 when you distribute. So notice I multiplied the 2 times both of those terms. Okay. So then we know that those two things have to be equal to each other. So 5x is equal to 4x minus 2. And then we're just solving for x. So x is equal to -2. I skipped some steps there, so if you have a question, you've got to let me know, please. Okay, questions on either of those? All right, what base can we use or should we use for this one? What do you think? 4? We could also use 2, but 4 will work, and I think 4 is probably easier. So let's keep this as 4 to the x. We've got to rewrite this 64. So 64 is 4 to the 3rd power. And then this 3 needs to get written out there also. So it's important you don't lose sight of those. So that's why I'm kind of trying to color code there to help you with that. Okay, so this is saying that 4 to the x is equal to 4 to the 9th. So x equals 9. Okay. All right, what base are we going to use here? 3. There you go. 3 to the 2x, and we're going to rewrite this 9 as 3 squared. That's the 9 raised to the 5x minus 4. And then we've got to distribute. So we get 3 to the 2x here, and we get 3 to the 10x minus 8. And then you're solving. So x is equal to 1. Okay. Now the practice you're doing, we're going to use this idea with what we're going to do tomorrow. That's what we're kind of introducing, letting that percolate in your brain a little bit before we use that idea tomorrow. But my math lab today is strictly on just the word problems, okay, the plugging in. So like I said, grab those laptops. You need that calculator for sure. Please read carefully. I'm going to float around to help you guys, kind of peek over your shoulder to see how you're doing, but read carefully, okay? Jake.